So let's look at this problem. We are given the joint density function of x and y and a function, sum of two random variables. The problem is to find the density function of the sum. So let me plot this, what we are given. So that's this, the joint density function of x and y is non-zero in this region, in this rectangle. All right, so as a curiosity, we could try to find the marginals. So fxx is integrate out y goes from -1 to 1, and this is given to be x. So that's going to be, so this integral will be x, then y goes from -1 to 1. So that turns out to be 2x, x goes between 0 to 1. And if you integrate this further on x, this you get 2x squared by 2, 0 to 1. So the area is 1 and it checks. And similarly, fyy would be fxy integrate out x 0 to 1. So this is x. That integral is x squared by 2, 0 to 1. So that's half y between -1 and 1. So that's uniform. And if you take these to product, you get back this. So we conclude that in this here, the joint density function is the product of the density functions, marginals, and hence x and y are independent. But that's not the question. The question is, how do we do the density function of z? So once again, if I plot the region where the density, so the density function is non-negative here, as we have seen. That's what is given to us. And z equal to x plus y is a line that passes this way, because when x is 0, y is z. So it depends. Notice that, so let's just think for a minute. X takes the values between 0 and 1. Y goes between -1 and 1. So if you look at this problem, here x goes from 0 to 1 and y goes from -1 to 1. So you can see the sum can go from -1 to +2. So there are multiple cases to be considered, and so we need to go through each of those cases. So essentially, a line like this is x plus y equal to z. But to see which case it refers to, so notice that when you put x equal to 0, y turns out to be z, and you can see y is the minus z is here. So c turns out to be negative. So this must be the case when z is between -1 and 0, a line like this, because this is the line. So that's one case. And another case would be like this. So this is also x plus y equal to z. But you can see here z is positive. When x is 0, c is here. C is positive and between 0 and 1. So this is z is between 0 and 1. So the final case would be, as you can see, a line like this. So this is also x plus y equal to z. But you can see z is beyond 1. So this must be z between 1 and 2. So we need to deal with these three cases differently. I mean, one at a time. So that's what I'm going to do next. So the z goes between -1 to 2. That's the thing. And we are going to deal with one at a time. And we'll find the distribution function, and then we'll find the density function from there, especially for problems, messy problems like this. So here we have, so this is the case we are going to deal with. So c between -1 and 0. And x plus y equal to z is this line. So we start with the distribution function of z. That's by definition z less than or equal to z. But z is of course given to be x plus y, so less than or equal to z. But z is now between minus 1, 1. So we are dealing with this case. And x plus y less than or equal to z is clearly this region. So it's either way we can integrate using vertical strips or horizontal strips. So if I use a horizontal strip here, x goes from 0 to, you can see from z minus y, and y goes from this place to this place. So this is z, and this is minus 1. So y goes from minus 1 to z. So this is fxy x comma y dx dy. So instead of simplifying, this is fcc. So I can just do the derivative here, right here, to find out the density function. So the derivative of the top limit. So I have to deal with this multiple times because you have limits on the integral. So the derivative of the top limit, which is 1, then when we substitute into this variable of integration, which happens to be y, you get 0 to 0. So that has no contribution. Derivative of the bottom limit, but that's a constant, so that's not going to contribute. So this essentially comes down to this way. Derivative of this inside integral z minus y fxy x comma y dx. Then the, and here again the same deal again. Derivative of the top limit with respect to z, which is 1. And wherever the variable of integration, we substitute the z minus y, the top limit, minus the derivative of the top limit. So that's 0 because it's a constant. And then the plus integrals stay the same, but the derivative with respect to z. So this is not a function of z. So this is the only term to make it simple. So this is going to be, remember, this function is just whatever is this. So this will be just a z minus y, this whole thing. So this is minus 1 to z, z minus y dy. So when I integrate that, I get a zy minus y squared by 2, substituted from minus 1 to z. So that's when you substitute the top limit, c squared minus c squared by 2. So that gives you c squared by 2 plus. And then for the bottom limit, you get minus 1. So that's plus z. And here minus 1, minus, and minus 1 squared. So that's plus half. So this, if you want, you can, if you pull out the 2 outside, you can see that this simplifies to this. So that's the answer for z between minus 1 and 0. So we'll put it together later. So let's go through each case. The next case is z between 0 and 1. So once again, we need to figure out the region. So now the line is like this, x plus y equal to z, but z is between 0 and 1. You can see here, so the intercept, this is the easiest way to figure out how the line would be. So once again, see the same argument as before. I'm not going to repeat all this. So all this will sort of go through. So this is going to be probability of z less than or equal to z, but z is given to be x plus y less than or equal to z. So that's going to be this region. So again, I can, if I do a horizontal strip, when you reach here, there is an issue. So it's better to do a vertical strip, it looks like. And you can do it in one shot because of this. And this vertical strips would slide easily from one end to the other end. So remember, so the first integration is on y. Y goes from minus 1 to z minus x, because y is z minus x. And x goes from here to here. So x goes from 0 to 1. Fxy x comma y. First we are integrating dy, then dx. So let's do the derivative again. So the derivative is going to be, derivative goes inside 0 to 1. Uh, so we need to do the derivative of this with respect to c. So the derivative of the top limit with respect to c, which is 1. Then wherever a variable of integration, we substitute z minus y. So that's going to be fxy x comma z minus y, minus derivative of the bottom limit. That's a constant. Third term is the derivative with respect to this. So essentially it's just this, z minus x rather, because this limit comes and sits here. So this is going to be, this integral is easy to compute because this term is just x. So this is x dy. I'm sorry, this will be with respect to x. So this is x dx. So that's x squared by 2, 0 to 1. So that's half z between 0 to 1. So that's also done. The last case is c between 1 and 2. So once again, the region is here. So now the line would be, remember, this is the line x plus y equal to 1. So this is z is between 1 and 2. So z will be like this. This is x plus y equal to z between 1 and 2. You can see the intercept to z is beyond 1. So once again, FCC is probability of z is x plus y less than or equal to z. So that's this region. So neither a horizontal or a vertical strip will do, but we can take advantage of the fact that the total area is 1, so we could integrate on this other region. So this is going to be 1 minus the integral fxy x comma y. X goes from here to here, so that point is z minus y to 1, and y goes from this point. At this point, z is 1, so x is 1, I'm sorry. So y is z minus 1 to 1. So let's take the derivative with respect to z. We can again do this mentally. So this is minus, this because of this minus sign. We must take care of the outside integral first. So the derivative with respect to the top limit, that's 0, minus the derivative with respect to the bottom limit. That's 1. So that's going to be minus 1. Then when we substitute the bottom limit into this variable of integration, notice that the outside, first we are doing with respect to x, then y. So the outside one is with respect to y. So when you substitute, instead of y z minus 1, this becomes 1 to 1, so no contribution. So then we go to the next term, which is minus the integrals, the outside limits stay the same. We need to take the derivative of this inside quantity with respect to z. So top limit, there is, it's constant, so that is 0. Then the formula says minus, so another minus 1. Minus minus becomes plus 1. The derivative of this with respect to z, that's 1. So 1. Then fxy, where the variable of integration is x, you replace by z minus y dy. So minus minus is 1, so I'm going to substitute this as z minus 1 to 1, and this is simply fxy z minus y. So that's going to be simply z minus y dy. So if you integrate that, that's a zy minus y squared by 2. We just have to substitute this without making mistakes, 1 and z minus 1. So if we go through this, this is going to, the top limit is going to be z minus half, and the bottom limit is minus z multiplied by z minus 1, and minus minus plus z minus 1 the whole squared by 2. And if you pull out half and simplify, this turns out to be half 2z minus 1 from here. Then I have z minus 1 here, so I'm going to pull out minus z minus 1 outside. Then you have, because of this 2z, and minus this, so that's becomes c plus 1. So if you put everything together, this will turn out to be, you can see here, this is just c plus 1, so that becomes, so this whole thing becomes c squared minus 1, because c minus 1 multiplied by c squared minus 1. So when you expand this, and then because of this minus, it becomes 2c minus z squared. And so if you pull out the z outside, this becomes c minus 2. So this is half c multiplied by 2 minus c, rather, because minus z squared 2c, so 2 minus z, which makes sense because z is between 0 and 2. So let me put all these results together. So FCC, if I look at the previous page, it's going to be half 1 plus z the whole squared for z between 0 and 1, and half when z is between 1 and 2, and it is half z multiplied by 2 minus z when z is greater than 1 and less than 2. This is 0 to 1. This is minus 1 to 0, 0 to 1, and 1 to 2. And if you plot it, you'll get something like this. So minus 1 to 0, it's a sort of a quadratic form. And when z is 0, it's half. So it goes there. Then it stays the same. Then when z is 1, it's half again. So that's good. And when z is 2, it's back to 0. And you can quickly integrate and see. I'm going to leave that this area is 1, verifying everything. So that's the density function of z for that given problem. Let me do one more problem. Suppose the joint density function is given by this inverse quadratic. Let's say so. They start with the density function is x greater than y in this region. Is density functions. The problem is find the density function of the ratio of the two random variables. So let's just hit it straight away. So the PDF of the FCC is probability of C less than or equal. So everything is positive here, x and y, z. So z is given to be x over y less than or equal to z. But because it is positive, we can rewrite this as x less than or equal to yz. And notice that x is greater than y, so z is always going to be greater than 1. So we need to draw the line x is equal to yz when z is greater than 1. Then of course that line would go like this because x is greater than y. So this is x equal to yz. And we need the region where this is the region where x is greater, this is the region where x is less, so we need to integrate out here in this region. So that's the big finding, that's the where this region is. So that region is going to be fxy x comma y, and if I take a horizontal strip, it sees it because this line is x equal to y, so you can see the limits. X goes from y to yz, and y goes from 0 to infinity. Uh, I'm sorry, 1 over greater than 1. So all this is, imagine this point is 1, 1. And let's say our coordinate system is here. This is x, this is y. Actually, the diagram should be drawn this way. So this is the region, and this is x equal to y, and this is x equal to yz for z greater than 1. And so the region where we need to integrate is this. So notice that this is the 1, 1 comma point. So y goes from 1 through infinity, the outer limit. Everything else is will be the same, even though this line should have gone from here, and this x equal to yz also would go this way. So which I redrew it here. So this is the line x equal to y. This is the line with the greater slope x equal to yc. So now if I do the derivative here, so this is 1 to infinity, derivative of the top limit, so that's y. Let's say the inside integral is, so I'm taking horizontal strip, so dx dy. So the inside integration is with respect to x. So x gets replaced by yz, comma y, and a derivative of the bottom limit with respect to z, no contribution. So it's basically it's just this. So now we can substitute the density 1 to infinity y. Fxy is 2 over, instead of x I'm going to put y squared z squared, then y squared, 1y cancels, dy. So we get 2 over z squared outside. Integral 1 to infinity 1 over y cubed dy. So that's going to be 1 minus 1 over 2y squared, 1 to infinity. Here you have 1 over 2 over z squared. So 2, 2 cancels, top limit 0, bottom limit 1. So we get the answer to be 1 over z squared for c greater than or equal to 1. So which is also a density function because area under that, so it's essentially like this. So that's it. That's the two problems on functions of two random variables.